Okay, excellent. Well, this is a big day. I'm very proud of Ryan, and he's been with me in my lab for 8 years,
6 years.
I think. Six? Okay. Well, he started as an undergrad and was exceptional. Did a lot of really interesting work, and I believe a turning point was when we were in a kayak together. I don't know if you remember this, Ryan, but
I kind of remember, yeah.
we were in a kayak, and you were going to take a job, and I was like, you should think about staying for a PhD. You're really talented, and somehow I guess we were in a kayak for about an hour or so with a bunch of the other students, and we and then somehow I think by the end of it you got convinced. So it was great. And then you came on and have done a fantastic job, as you're going to all hear today. He was he's been a star in the lab and extremely well popular. Also has led some major efforts off campus and at conferences. He has been the social chairman at several conferences, including Coral, and a ringleader in several of our parties and events. Also been a big help around the bear community, and he's also, I would say, one of the best presenters that I've worked with in many years. He's really got a style and a way of presenting that's extremely professional, and as you'll see, beautiful images and just compelling arguments. And you'll see it today. I think this is a perfect capstone. I had a glimpse of what the slides and his talk is going to be, but you're in for a treat. So with that, I will say I'll turn it over to you, Ryan.
Okay. Thank you so much for the kind introduction. And it's been an absolute pleasure to be in the lab and be at Berkeley for as long as I have been. And I'm very excited that all of you guys showed up. Half an hour ago, there's nobody here. I was like, oh no. But full house is great. All right, so let's get started. So we know that when humans are controlling robots, they're capable of incredibly dexterous things, right? You can see, assembling this thing that could be on a factory, right? But you see that a human is controlling the strings, right? Like puppeteering this system. This is a video out of Stanford. This is a popular paper called Aloha. But this has also been the case for decades. Even in 1957, we had a leader-follower system where we can dexterously light a woman's cigarette with someone behind the strings doing this leader-follower system, right? But I still have to do my own laundry, right? What gives, right? Where are the robots? Why aren't they folding my laundry if clearly the hardware is capable of doing these dexterous tasks, but the intelligence isn't there yet, right? Now, in parallel, there's been a really exciting trend in our friends in vision and language who are also on the floor. Large-scale supervised learning has blown everyone away, right? ChatGPT, Gemini, I mean, you have to be living under a rock at this point to not have heard of this kind of thing, where the idea is, you do supervised learning on the scale of the entire internet, everything a human has ever put on there, text, images, or whatever it is, and you get these really amazing results that come out. And you could ask the question, well, why don't we just do that for robotics? Let's just collect a bunch of human control data and let's just imitate that, right? Well, there's a couple problems that come up. One is distribution shift. What does that mean? That means that because the robot is actually executing actions in the environment, right, it can make these small errors and eventually visit a state that the human never visited when it was operating the system, right? You're not trying to imitate a static data set, you're actually trying to do things in the world, right? So this turns out to be challenging. There's a related problem of the long tail, right? So the long tail is all these situations that have a very low probability of occurring, but they still can, right? So they're unlikely to be represented in your data set, But when they do happen, you want to be able to deal with them, right? A moose crossing the road for the first time or something, right? And even worse than that, we have a data problem, right? So we're not fortunate enough to have the internet lying around with all the text and images on it for robotics, because who would put robot control data on the internet, right? So we have this chicken and egg problem where, on the one hand, robot learning needs big data from being deployed at scale, but on the other hand, robot learning is not yet reliable enough to be deployed at scale. So this question I was really interested in my thesis was, well, is it possible to shortcut this paradox somehow? Can we reliably deploy robot learning systems today and at scale? Well, we don't have to philosophize about this, because in recent years, we are seeing increasing amounts of large-scale robot deployments out there in the real world, in applications ranging from self-driving to e-commerce order fulfillment. So, what's their secret? How is this possible? Well, one answer is to fall back on humans, right? So there's these companies that allow you to, even for driving, remotely intervene, take over a vehicle. In these kind of edge cases that the system is not 100% capable, if you're able to hand it off to a human to do just that part of it, you can kind of bridge this gap, right? But of course, this isn't trivial, right? There's still challenges that come with this idea, right? In particular, Cruise has been having a hard time, and Waymo could get stuck in the fog and whatever. Although these systems are very, very capable now, that long tail is always elusive, right? But this is very interesting, right? Because this idea of falling back on humans kind of subverts what we're used to thinking about when we think of robot autonomy, right? So we're accustomed to thinking of it as this binary decision variable where either the system is fully teleoperated, fully under human control, think like intuitive surgical, something like that, or it's fully autonomous, fully robot control, and there's no in between, right? But if you allow humans to come in some cases, then you introduce this whole spectrum between these two extremes, where on the one hand you have 100% human control, on the other hand you have 100% robot control. And in between these two, we can call this, for lack of a better term now, supervised autonomy. Okay, so what does supervised autonomy mean? It's autonomous, but it's also being supervised in some sense. And there's a couple appealing properties of this. One is that we're blurring the distinction between what we call train time and test time, because there's two things going on, right? One, the human is coming in after the robot is already executing its policy, and now the performance of your team is going to be better than just that robot alone. And at the same time, whatever data that human is providing in giving these interventions is going to go back in, refine the system so that the next time the robot sees it, it won't make the same mistake. Now there's some nice properties of this. One is that we can continuously approach full robot autonomy over time. You don't have to jump the step function all at once. And if you're clever about it, you can have a single human supervising multiple robots, right? You don't need to have a one-to-one connection. And most importantly, it's realizable today. So if you dig into the fine print of what that Cruise article said, these vehicles are supported by a vast operations staff with 1.5 workers per vehicle that intervene every 2.5 to 5 miles remotely. So they are using supervised autonomy and not a particularly scalable form of it, right? More humans than robots. But it's not just Cruise, right? There's all kinds of cases. And in the words of The Atlantic, people are the hack that make automated systems work. So I'm going to propose a recipe that I've been considering for achieving this paradigm, right? And we can call this scalable lifelong learning, right? And there's going to be 3 components to this recipe. There's going to be supervision on demand, fleet supervision, and large action models. Okay, so let's go through each of these. So behavior cloning is the standard way to go about this, right? What does that mean? Collect a big data set of the human doing the task, have the robot imitate that, just do supervised learning on that. But what happens often is this distribution shift problem that we were mentioning earlier. Because you're not allowing the robot to execute what it has learned, it may encounter some failures that perhaps it doesn't know how to recover from. Now, the conventional way to deal with this is an algorithm that was proposed over 10 years ago called DAGR, dataset aggregation. It's a very influential algorithm, both theoretically and in practice. The idea is very simple. You just let the robot execute what it has learned, and then you're going to collect additional human data on the states that the robot actually visits rather than the ones that the human visits. Intuitively, say the robot knocks over a mug. now you can go in and pick it up, right? Because the human never would have done that when they are doing their mug manipulation task, right? Now there's a variant of Dagger that has become popular in recent years, which is called interactive imitation learning. And the idea of interactive imitation learning is that at any given time, either the robots will be in control of the system, pi r, or the human will be in control of the system, pi h, right? And we'll switch control with some switching policy omega, and basically the human come in these edge cases or whenever else is needed, take over control, and you can intelligently switch between these two things, right? And again, there's two things going on, right? There's the human-robot team aspect, there's the data collection aspect. Now, it turns out that deciding what this omega switching policy is turns out to be really challenging because there's two competing objectives that you have to consider. One, if you let the human do everything, then you can have very high performance at the task, but also very high burden on that human supervisor. He has to be doing everything, right? But on the other side, you'll have no burden on the human, right? You don't ask him for any help, but then you have low performance, right? You don't get any assistance there. So how do you strike this balance? Well, one family of approaches that deals with this is called human-gated interactive imitation learning, and the idea of that is that the human is going to be the one that is supervising the system, watching what's going on, and when it decides that the robot's doing something that it shouldn't, it can come over, take over control, help it, and then give back control, right? So the human is subjectively deciding these switching points. And this can work quite well, and it's an intuitive way to do this, but it's not very scalable, right? So say you have 10 robots you got to watch all at the same time. Now there's only so much I can look at, right, before I get overwhelmed. And also if I wanted to do this for a very long period of time, say like the robot's just running 24/7, I don't want to have a human watching that the entire time it's running, right? So the alternative to that is robot-gated interactive imitation learning, kind of a mouthful. But the idea here is just that the robot is the one that is going to itself decide when he's going to ask for help, right? So he's going to say, you know, I don't know what I'm doing. Can you come in and help me, right? So this is what I mean when I say supervision on demand, because the robot is the one that is asking for help, and the human could be doing something else. It could be helping another robot, for example, right? But of course, this begs the question, when should the robot ask for help, right? Turns out that this is a very hard question to answer. And the reason is because it's this kind of unknown where the robot doesn't even know what it doesn't know, right? And the quantity that you actually want is something called the value of information, the VOI, from decision theory. But there are all these proxies for the VOI that you can have because the VOI is intractable, right? In any real world setting, especially the high dimensional robotics, trying to do that in closed form is just basically impossible. So what prior works have done is estimate various proxies for this VOI, such as novelty, uncertainty, risk, action discrepancy, things like that. And then when these values are above some kind of threshold, then you can say, I need help, right? So our contribution to this line of work is something called Thrifty Dagger. And Thrifty Dagger was a paper we presented at Coral, Conference of Robot Learning, a couple of years ago, accepted for oral presentation. And the idea of Thrifty Dagger is that we're going to consider these two quantities, novelty and risk, right? So novelty is how out of distribution are you? How new is the situation relative to the data set that I have? Whereas risk is how likely am I to fail at my task? In this case, say crash the car. And the observation is that typically these two things are conflated, where novel situations are also risky by virtue of being novel, driving in snow for the first time, something like that. But there are actually off-diagonal terms as well, states that can be novel but not risky, wide open dirt road for the first time, but you can't crash into anything, for example, or risky but not novel, right? I'm driving this tight cliff. I've done it before, but perhaps I don't trust the system to get this exactly right, and I might, go off the cliff or something, right? So for how we actually do this novelty estimation, what we do is we train an ensemble of neural networks bootstrapped on different subsets of our training data. The idea being that if I give a new data point and none of my networks have seen it before, they're going to disagree more than if they have seen that data before. So you can measure that variance in their action output and use that as a proxy for how new is the state. Now, interestingly, multimodality will be a false positive for this, but we'll revisit that soon. But this can work quite well. And for risk estimation, we actually use reinforcement learning. So what we do is we train a Q function to estimate the discounted probability of accomplishing our task, right? So we assume there's some kind of indicator that tells us when we have completed our task, a a goal conditioned, assume the task is goal conditioned. Then what you can do is based on your prior experience in executing this task, whether the human's doing it or the robot's doing it, you can say, under my current robot policy, how likely is it that I am going to converge to this goal set? Then your risk is going to be 1 minus that, or how likely you are to fail, right? Now you can synthesize these two criteria so that your novelty switch is kind of like your unknown unknowns, where this is a data point you don't know what to do with, and your risk is your known unknowns. Like, I've seen this before, and based on what I've seen, I know I can't do this, for example. And there's a really nice property of this decomposition, which is that that risk critic is only queried within its training distribution, right? So you only need to rely on risk when your state is not novel, right? Because if your state is novel, it will already have asked for help, right? But if it's not novel, then you know I've been here before, I can trust what my risk critic is saying, and he says, I should ask for help, for example, right? Now the upshot of all this is that, kind of amazingly, robot-gated intervention criteria can rival human-gated ones. So consider this cable routing task where you have the surgical robot that's kind of navigating around all these pegs. What it's doing here, this is all image-based, right? Just straight pixels to torques, or pixels to deltas. What you could do is you could have the human just keep watching it and say, oh, it needs help now, I'm going to help it. Or you could have the human step aside, do something else when the robot asks for help, give a little intervention, and so on. These two can actually be very comparable, right? And that's interesting because the robot is not requiring the human to constantly be there. So both in terms of autonomous success rate, means no human aid, supervised success rate, these get very comparable success rates, and with additional amounts of human control, right? So this is a percentage of the episode that was human controlled. At training time, this is say like 25% of the episode, but at execution time, which is after I've trained the system, I'm still allowing humans to come in and help me. You see that the amount of help that it asks for is way less, right? That means it has learned to not superfluously ask for help in the same kind of situations that it has before, right? So that's a good sign for scalability, right? And it's only asking for help in, say, 1 to 5% of the episode's length. We also did a user study to further see how well this works. So here's the idea. We're going to have, we had 12 human subjects performing this task where on the one hand, they're going to try to supervise these 3 robots that are doing this task and simulation. And at the same time, they're going to try to play this memory matching game where there's these sets of face-down cards. And the idea being, if your robots are always pestering you for help, you're going to have a hard time making progress on your memory game, right? And again, what you see is that if you're clever about how you balance, task performance with human burden, right? You can actually benefit both human task performance and robot task performance, right? So how you do that switching actually does matter quite a bit, and you can see kind of a pretty dramatic improvement in the performance of your team, right, with comparable amounts of human data. So that's encouraging, and also in survey responses, people indicated that it was less frustrating, less mentally demanding than the alternative. Okay, so that's supervision on demand, but there's a second notion of supervision on demand that I want to mention, which is remote supervision. So the internet is a thing now, it works quite well. And because of that, your human supervisors don't even have to be physically present, right? Your supervision on demand could be anywhere on the globe, right? And Isaac Asimov, a popular science fiction writer, predicted this in 1950. He's like, oh, look at this room, it's robots only, 5 men act as overseers, they don't even stay in this room, right? And now this is actually the case. So this was a project, I won't go into too much detail for sake of time, but this is a collaboration we did with Google DeepMind where they had this robot work cell in their office in Mountain View. We were here in Berkeley, and we did this entire research project. I never even laid eyes on this robot, touched it or anything. We did this entire research project. We were like manipulating t-shirts, folding clothes. They were sending back images of their setup at 10 hertz, and we were giving back control actions. This whole thing, is very doable today, right? Okay, second component, fleet supervision. So we talked about how this omega switching between pi h and pi r, deciding how to do this is already a challenging problem, right? Now what happens if we do this? Now we have a pool of humans. We have multiple humans that could help. We have a whole bunch of robots, probably a lot more robots than there are humans. And we're trying to decide, how do we do this matching problem? How do I give the humans to the robots that need the most help if they're outnumbered 10 to 1, something like that, right? So this is interactive imitation learning, with multiple humans, multiple robots. Now, we looked in the literature, we're like, okay, surely someone has thought about this, and this didn't exist. It didn't exist. No one had studied the setting yet. We're like, huh, that's very interesting because we have all these existence proofs for it in industry. Like clearly people are doing this for things like self-driving and so on. Why hasn't it been studied? Why isn't there like a way to actually tell what's the best way to do this allocation problem, right? Now there have been fleet learning works in industrial research, a lot of good works out of Google DeepMind, where they have these massive arm farms or mobile robots that are, for example, doing reinforcement learning or something like that, but usually the emphasis is on something different than this human assignment problem. So that motivated this follow-up paper, Fleet Dagger, and this was the following year at Coral, also accepted for oral presentation. And the idea of Fleet Dagger is let's really make the tools to even study this setting, right? And try to like make some decisions about this, right? So first thing we do is we establish the first formalism for interactive imitation learning with multiple humans, multiple robots. The idea here is you have some humans, they're being allocated through some allocation policy omega to the robots in your fleet that need the most help at any given time, right? So say red, green, and blue in this case, and then that data goes back into the data set and they're continually learning from that. And each robot can actually learn from the other robots and so on, right? Now, let's touch on the math for a bit. Don't be too afraid. It's not too bad. We're going to model each of our robots as a Markov decision process. They're all going to be identical except for the initial state distribution. So they might have different initial states. And what we can do is we can turn that into one big vectorized Markov decision process where each individual state is actually the states of all your robots, and they're all sharing the same policy, pi. And you can compose their transition and rewards appropriately. And what we want to find is we want to find that omega, which is a mapping from the states of all our robots at a given time and their shared policy, pi theta t, to a binary assignment matrix, alpha, that indicates basically which human is controlling which robots at any given time, right? So just those ones means human I is controlling robot J at a given time, right? And the objective that we want to optimize in this setting is something we call the return on human effort, right? So we want to find an omega, an allocation policy, that is going to maximize the performance of our fleet at whatever task they're doing, but normalize that by however much human effort it took to get to that level of performance. Right? So you want to reward, task performance, you want to penalize human burden, right? That Frobenius norm in the denominator is really just counting the number of ones in all those alpha matrices over time, right? And how this gets complicated is this allocation affects the learning process, which affects the allocation, and there's like this coupling going on. So this can this is not a trivial optimization problem to solve. Now there's a few modeling assumptions, of course, because it is a model. And some of these that are worth mentioning. One is that the humans we're assuming they all have a homogeneous human policy, so they're all executing their control in the same way. Not necessarily realistic. We'll revisit that assumption soon. We're also assuming the robot environments are all independent. So think bins on an assembly line, lanes on a highway. Not so much like a robot swarm. There's a lot of great works on robot swarms, but I'm trying to distinguish between robot fleet and robot swarm. Robot swarm, typically a lot of low-cost robots acting in a shared environment towards some shared goal, kind of like a colony of bugs, for example, right? Now, as part of this formalism of interactive fleet learning, there are other, we show that it's actually general enough to include a whole bunch of different approaches, right? So including Thrifty Dagger that we just mentioned, including Ensemble Dagger, all these algorithms can be adapted to this fleet setting with an appropriate choice of parameters, and then we can actually compare them against these other approaches, right? So this is general enough to handle existing algorithms as well. And then a big contribution here was this benchmark environment. So again, a big goal of this project was we want to even make it possible to evaluate in a standardized way whether one allocation policy is better than another. And to this end, we released this benchmark on top of NVIDIA Isaac Gym, which a couple of years ago for the first time allowed us to simulate hundreds or even thousands of robots on a single GPU very efficiently, right? So usually that was used for reinforcement learning. In our case, we found that was very useful for imitation learning, where you have, say, 100 different robots. You want to compare what's going on here. Now, when we used this benchmark, we did simulation experiments with 100 robots doing things like manipulating cubes in their hands, or humanoid locomotion, or legged locomotion. And we find that the allocation does matter quite a bit in terms of how often these robots can complete their task, how often they fail, how long they're left idle. You can see that the return on human effort on the right, this is a little bit blocked, but the return on human effort on the right is increasing over time. What does that mean? That means that if successes is going up and human effort is tapering off, this return on human effort is a ratio, so an increase in the ratio means you're getting more and more efficient, right? There's other cool things you can do here where you can, for example, say I have 100 robots and I want to determine how many humans do I need to get the most bang for my buck, so to speak. Well, I can just run an optimization over the number of humans m, say 1, 5, 10, 25, 50 humans, see how much they benefit me. And there, the return on human effort, again, will be, say if you have more humans, of course, you're going to have more successes, but then you're also going to lower your return on human effort because you have extraneous human help. So again, like 10 here strikes the best balance between these two objectives, right? And you could do other optimizations you might care about. Now, we also did physical experiments, right? So the physical experiments, the idea is, I want a way to, a big goal of our lab is you don't want to just do things in simulation. You want to show that it actually works in the real world. Well, we don't have a war chest of money lying around. We don't have 1 million robots. What we do have is these 2 ABB Yumis that are in each of our labs, right? We have one right there in the auto lab. We have another in Echeverry Hall. And what we did is we repurposed these 2 robots into 4 robots where each arm is acting as an independent robot system, right? So you just mirror the image that one arm is getting, and they all don't know about the others necessarily, all operating simultaneously, doing this, in this case, a block pushing task. They're not aimlessly pushing it. They have a picture of what they're looking at. They procedurally generate a goal region they want to push towards, and once they reach that region, they can just resample it and then go somewhere else, right? And then we have 2 humans that can come in remotely, do some teleop over the internet, in the case that these systems need help, right? And again, we observe similar trends to the simulations, albeit with a little more variance, because there's real-world results. And then the last bit on this real-world part, there's another initiative in our lab called fog robotics. Fog robotics is a generalization of cloud robotics, where robots typically have limited compute and data on the actual system, but the cloud has all this data and compute. Could you seamlessly connect those 2 things, right? And it turns out you can. And we did a collaboration with the Fogros team on extending Fogros to Fogros SGC, secure global connectivity. The idea being, if you had networks that were distributed all over the globe, could you seamlessly connect the whole thing as if it's a local network? And with this, you actually can. So you can implement this in ROS, the robot operating system, with Fogros, and you can do that same fleet experiment we just did with a compute node all the way in Carnegie Mellon, 3,600 kilometers away, whole thing running in real time, fully in ROS. That works fine. Okay, so now let's go back to that human policy, right? So we have pi h. We're trying to decide, we said earlier we're going to assume that all these humans are operating the same way. Well, that's not necessarily realistic, right? Because different humans can have different preferences. So this motivated a follow-up paper called IIFL, Implicit Interactive Fleet Learning, last year's conference on robot learning in Atlanta in November. And the idea here is, well, what if different humans have different preferences, right? They don't want to teleoperate the robot in the exact same way. Maybe even a single human changes his mind one day and is like subtly doing things unconsciously that are different than the day before. We don't want this to completely mess up our system, right? Now, fortunately, this has been an independent topic of interest in the robot learning community, which is learning from multimodal data. Turns out it's very challenging. If you have say you want to go left or you want to go right, if you average that out, you just end up going nowhere, right? But there have been these works in the field. So recently, the latest, greatest way to do this is called diffusion policy, a huge breakthrough last year. At the time we were doing this, it didn't exist. If I were to do it again, I would use that. At the time, we used the next best thing, implicit behavior cloning. So that's what's going on in the middle here, which is saying that instead of just mapping your state to the action that you're going to take, instead you're going to map your state and some corresponding action to some energy value, which is how much do these two things match, right? So how, and this allows you to, for example, specify a whole circle instead of, you can have different actions paired with a single observation, right? Now there's something that becomes tricky here. So the way that you train these things, you train this implicit energy-based model where the probability of taking some action, given that you're in some state, is equal to your exponentiated energy, but normalized by this function z, the partition function. This partition function is computationally intractable. This makes these things very hard to train because what you're doing is you're summing the energy of all the possible actions you could take, and that could be like a very gigantic space, right? And this is posing problems for us because we were trying to do something like our uncertainty or novelty estimation from earlier, where we train, say, an ensemble of neural networks. Now that doesn't make sense anymore because multimodality is a false positive. If two of your subnetworks are saying radically different things, that doesn't necessarily mean that they're uncertain. They could just be equally certain about two different ways to go about it, right? So what we did is we found that there's this notion called, there's this tool called Jeffreys divergence. Right, so this is based on KL divergence, which is a popular metric in machine learning, but this is a symmetric KL divergence. So it's the KL divergence is a measure of the distance between two probability distributions. This is a metric that symmetrizes that. And there's another one called Jensen-Shannon, but that doesn't have this property either. The property that if you apply the Jeffreys divergence to a pair of implicit models, amazingly, your partition functions just cancel out by symmetry. And actually, Gaurav was around somewhere, found this, and he was like, wait, that doesn't make any sense. How's that possible? And we were like, wait, did we just like completely get rid of these z functions? And it turns out we did. So what this is doing is you can think about this as a generalization of that ensemble idea, where instead of comparing the point action outputs of like what one model did versus the other, we're comparing the entire action distributions of what one model did versus another. So you're training an ensemble of two networks in this case, and you can efficiently compute the distance between these distributions using this technique. So what happens is you can apply this for something like, say, you say you have 4 different ways to do a task, right? In this case, stacking this cube. You can have all these kinds of pairs of antipodal faces you could graph. Even for a single cube pose, you grasp it like this, you could grasp it like this, you could turn your hand around, right? There's 4 different ways to do it. If you have 4 humans doing that and then you throw IFL explicit methods at this, they can really struggle with trying to figure out which one should I do. But you use something like IIFL, now you can dramatically boost your performance and handle this kind of multimodality. Importantly, even over what we call IIFL-R, which is the same IIFL strategy, but instead of Jeffreys divergence, we're just randomly assigning humans to robots. It turns out how you do that allocation matters, right? And then physical experiments, again, we have that block pushing from earlier, but now we add an obstacle to the center of each workspace. And now we're going clockwise or going counterclockwise around this obstacle. And again, this would confuse an explicit method, not necessarily an implicit one. OK, last component of our recipe is large action models. So what does that mean? So we're all familiar with these large models now, large language models, large vision models. So say we have a scalable way to collect all this data. We can grow our data set over time. We have this big data. Is it possible to even learn from that data? Is there something that can process as much data as we can throw at it and just like soak it up? And the good news is there's evidence from vision and language that these modern models can ingest trillions of tokens and be fine, right? You can just keep throwing data at it. Right? There's research on scaling laws. There's a scaling law called chinchilla scaling from OpenAI that suggests that a trillion parameter model, if you want to train it in a data optimal way, you need to give it 20 trillion tokens, right? So the model is not the bottleneck, right? The data is, right? So the model we don't necessarily have to worry about. So now we have large language models, you have large vision models. What about large action models? What about for robotics, right? There's different ways different terms you could call this. You call it a vision language action model. That's sometimes the case. So one effort I'd like to highlight is RTX, which has like 1 million authors. I'm like author 100. But the idea here is that it's technically fleet learning, right? There's all these robots that are distributed around the globe, that are distributed in terms of hardware. There's different embodiments, but you're still pooling all that data together, training one common policy. So this was really about, let's collect a big data set, over 1 million trajectories, 22 different embodiments, 34 different labs, throw it into a big model, see what happens. And the evidence seems to indicate that these large action models can be effective data sponges, that they can kind of absorb this data that you're throwing at it and continue to get better. Now, of course, there's a long way to go, right? This is still like 70, 80% or whatever, but it's a step in the right direction, right? It's an encouraging proof of concept that maybe, we can, if we had enough data, keep continuing to scale these things. And so some lessons from large action models is that from that RTX effort is, if you want to further facilitate scalability, something like your RTX model, it can be multitask and it can be cross-embodiment. And that is nice because now you don't have to retrain your policy every time you change your task, every time you change your hardware. Rather, all those robots can come together and train a common brain, right, so to speak. So that will further facilitate scalability in this case. Okay, so to briefly recap how we did these assignments, Thrifty Dagger, supervision on demand. Fleet Dagger, IIFL, was fleet supervision. RTX for large action models. Okay, so now let's talk about where can we go from here, right? Well, one thing you could do is I never specified that policy in our IFL model has to be a particular way. You can just swap in the latest, greatest policy and still embed it in this framework. So for example, you could upgrade IFL to diffusion policy. You could use a multitask language condition policy like RTX. You could bring in reinforcement learning, so your policy update mechanism isn't just doing supervised learning, but also learning from its own past experience, right? There's all interesting ways you could take this. Another interesting way, another interesting extension is to give feedback with language, right? So you don't, perhaps you don't actually have to come in and remote control the system to correct what the robot is doing. Maybe you can just tell it, hey, you're like off to the right a little bit, right? And that's kind of what this human is doing in this case. This was out of Google a couple of years ago, where he's just, you can see the future of robot supervision here, where he's just saying like, oh, you're off a little bit over there or whatever, right? And that could be easier to provide than low-level teleop. Of course, the hard part is grounding this in actual control is challenging, but there's some cool works that are coming out that are tackling this. For example, Yell at Your Robot, which is kind of fun, from Stanford and Berkeley. Okay, another angle, you've been talking about data efficiency. Can we, how far can we push this, right? We were saying we want to save human effort. We don't want to burden the human. Imitation learning can require a lot of human data, right? So some works have hundreds of thousands of demonstrations, many, many hours of data collection. You can ask yourself, well, how much of that data is actually redundant? Like say you're doing one demo versus another, maybe 90% of it is the same thing, right? So why spend all that time doing it if there's a way to save time in some sense, right? So there was a paper out of NVIDIA's robotics lab, MimicGen, last year, where the idea is, okay, let's just collect a very small number of human demonstrations and then use that to synthetically generate a really big data set where we're going to transform those trajectories into new poses, right? And get kind of generalization for free in this sense. And I was there for the summer last year. I was fortunate to work with Ajay, who was the first author of MimicGen, and we extended that to interventions, right? So the Dagger setting. So if you have, say, a correctional intervention, now that can be even more burdensome. You're deploying the robot policy, you want to let it execute, then collect a little intervention. In order to show it how to recover from every possible mistake it can make, that's going to take a while. But if you had some way to synthetically generate these interventions, that could save you a lot of time, right? So I won't go into too much detail because for sake of time, but what this allows you to do is say you only collect 10 human interventions, right? Very, very doable. It takes like a couple minutes. You can automatically expand that to like 1,000, 10,000, and then you can improve your robustness pretty dramatically, say like 39 times in some cases using this idea. Okay, another extension is autonomous robot data. So you have your whole fleet running, you have human data, you have a way to collect that human data, process the human data, but all these robots are generating their own data of like what they were doing when the human wasn't helping them. What do we do with all that data, right? It seems like a shame to throw that away. Is there a way to use that? So you could do reinforcement learning. You could use like the Q-risk idea we were doing earlier, some kind of offline RL thing. You could train dynamics models. So this was something I briefly did in my master's for deformable object manipulation, but you could also do it for other cases. I think perhaps goal condition diffusion policies would be a good candidate for inverse dynamics models, right? Where I think this is worth revisiting these days. And then the last extension here, better allocation algorithms. So I mentioned, we made progress on this, but it's still like a starting point, right? There's still ways to go, in part because out of distribution detection, uncertainty quantification in machine learning is still an open problem. It's hard to know that unknown quadrant, right? Good news is community is actively working on this. And there's this paper that's going to be at ICRA this year, 2024, that uses Thrifty Dagger as their main comparison. They extend Thrifty Dagger, and they also adopt our return on human effort metric, so it's nice to see that people are building on this work and continuing to push it, right? So that's the main part of the talk. I just have a couple concluding thoughts at the end. So it's a very exciting time to be in robotics. There's this energy in the air that we haven't had for a long time, that we have Waymos that can take you anywhere in San Francisco that work very reliably. You have robot dogs, robot lawnmowers. You have humanoids that look like they came out of science fiction movies that are starting to be developed. And there's this excitement that the GPT moment for robotics is just around the corner. A lot of investment, and so on. And whether this that these humans can finally be, that these robots can finally be useful in our homes, in our factories, doing the things that we don't want to do, the manual labor, right? Now, whether this actually comes true in the next few years is something that we'll find out, right? I do think there's definitely a lot of reason for optimism, but maybe a cautious optimism, right? There's still a lot of research to be done, but there's a lot of evidence that cool things are coming, right? And on a more personal note, this is the end of a long journey for me. So I was an undergrad here, I was a master's student here, and then I was a PhD student here. And I came to Berkeley as a freshman in 2016, 18-year-old knowing nothing about the world. And I spent my entire adult life here so far, 8 years of my life. And I learned so incredibly much. I just felt like I was just soaking up all the information I could, right? I love learning. I wouldn't have done a PhD otherwise, right? And I learned so much from my teachers, the amazing curriculum that Berkeley has. I learned so much from my peers, my lab mates, the senior grads that graduated before me, the undergrads and master students that I've been able to mentor, from my advisor, Professor Goldberg, who taught me how to think like a scientist, right? And I just have a lot of gratitude for this place. It's a very special place, and I think it'll always feel like a second home to me. So that's my talk. Thank you so much for your attention, and thank you to all my great collaborators over the years, without which none of this work would have been possible.
Bravo! Excellent. I imagine there's thunderous applause over there right now.
Yeah, I don't know if the microphone picked up on it.
I think you got filtered out, but it was so great.
Yeah.
Great job. Yeah. Great job. Should we open up for some questions?
Yeah, happy to take any.
Okay. Okay, I have a couple, but I'll defer if someone there wants to ask one.
Anyone?
Or online? Anyone on Zoom?
Yes. Robot apocalypse? Yeah. That's a good question. Okay, I don't think there's reason to. If you ever work with a robot, you're gonna realize it's very far away. You're like, what is it doing? This is so stupid. Like a baby could do this, right? There's one. So I think we don't have to sound the alarm yet. And the other case is, well, there's a lot of research on alignments. How do we align these robot incentives to do what we want them to do? And yeah, I mean, I don't think it's likely. I think it's more like a science fiction doomsday scenario than an actual thing. But I mean, in all cases, whenever you make a technology, it can be used for good or evil, right? It's like a hammer, right? There's any kind of use case you could have for it. And our goal is to develop these for the benefit of humanity, right? Not for their harm. Yeah. Someone once said the goal of robotics is to take the robot out of the human, do the, the mechanical stuff. Yeah.
Great presentation, Ryan. I just
Thank
wanted to
you.
ask, this is like more of a personal question.
Sure.
What's next for you? Like, what do you want to do now?
Big reveal. Yeah, so I signed as a research scientist with Apple. So I'm going to be working on robotics there. So it's going to be exciting stuff. Yeah. Thank you. Thank you.
Great. Ryan, can I ask you a couple questions?
Yeah, sure.
Oh, good. So I really like this point you're raising about this new paradigm where we're collecting lots of data, and you're thinking deeply about how that gets done. And I'm curious, when you think about Dagger, it's so effective, right? Just being able to provide the corrections rather than just more examples, right? And so you let the rollout happen, you see where the robot is having trouble, and then you're providing corrections, right? We know that's very effective. Now, that hasn't been entertained in these big projects, as far as I know, RTX, right? Could it be? And I guess that's what I'm curious if you have some thoughts about that. Maybe it also intersects with your thinking on fleet learning, because obviously, you're going to have a lot of robots. Just managing doing this in real time is tricky. I'm just curious if you've thought about how could we provide like a Dagger-like supplement to these data sets.
Yeah. That's a great question. So there's a lot of it's become popular to just collect offline data, just do behavior cloning and hope for the best, because it's just a lot easier to just collect data sets, train on that. But I think you're 100% right that the next step in things like RTX is deploy the policy that it has learned, allow humans to come in, do corrections, and that can only improve it, right? There's no way that this online data for giving more examples of what you should do in new situations could hurt your policy. It can only help. And I think one interesting way to incorporate this Dagger-like thinking into even offline data collection, where you're not doing any further refinement after the fact, is to anticipate what failure modes the robot could encounter, deliberately go to those failure modes, and then show it how to recover from that. So there, it would take the exact same amount of effort as your usual offline behavior cloning does, but now you're allowing it to show example. You're allowing it to see how it could fail, how it could recover from that. You're bringing this Dagger philosophy into the offline realm. So maybe you could get a best of both worlds there.
Good. Yeah. Okay. Oh, I really like that answer. That's great. I think it's very interesting. Have you seen the newest result? The
Aloha Unleashed.
Aloha Unleashed. Did you see that from last night? Okay.
I did see that. Yes.
Okay. So I was really studying those, and I loved it because it's interesting. What is there? There's repairing a robot gripper, tying a shoelace, and hanging a shirt, or basically smoothing out and hanging a shirt. Now, one thing when I looked at those is that there were some nuances where the specific parts of those tasks where you could see where the failures might happen. And it seemed as if there was some nice recovery going on. If you notice, with the gripper, right, there was that one little part at the beginning, it just struggled to get it in there and it kept retrying it.
Right.
And similarly, there was a retry and the folding of the shirt, putting it on the hanger. The second gripper had to pick it, and it missed a few times, but kept trying until it got it. So those are little pieces, relatively of the whole assembly or the whole task. Those are probably less than 10%. So what you're saying is, like, if we could identify those critical segments of the task, and really drill down on those, because those are where I'm sure the failures often happen, and get those policies really tuned up around that, then you probably get, a good performance. And that's really interesting, because today what people are doing is, well, if it doesn't work, just give it more demonstration. So you start over with the crumpled up t-shirt, you start all over, do the whole thing, you do all this 95%, which has kind of already been learned, but you want to concentrate on this 5%. So can you just zero in on that, right? And I think
that's exactly right.
that's
exactly
kind of,
right.
yeah, that's what you sort of said, which is let's look at these failure modes and try and even identify them actively, which is really interesting, right? Like a systematic way of finding them. And then really reinforcing those somehow with the demonstrations or possibly even other things, recovery modules. So I'm just curious if you have some thoughts on that.
No, yeah, I 100% agree with that. So typically you could call them like bottleneck regions, which is like regions of your task through which it's hard to make progress. But if you don't pass that region, you're just gonna catastrophically fail. Like little narrow bands of acceptable states that you have to pass through. And maybe 95% of your tasks maybe is just moving through free space or something that's very easy to do. You're wasting a lot of time collecting that entire demonstration when what you really care about is drilling down on that bottleneck, finding out all the possible ways to go through there. And with the exact same amount of effort that you could have spent, just rotely collecting more and more demonstrations, I think active data acquisition, collecting data where it matters, when it matters, how it matters, is very, very important, and I think will be a big piece of the puzzle going forward. Yeah.
Great. I like that. I like both those terms you just came up with. Really think of those as bottlenecks, and then actively collecting data. Right. It's really, I think that's definitely going to be part of the answer. Okay, great answers. All right. Anyone else have a question for him?
Angie.
Angie?
Are there any other real questions before I talk? All right, here we go.
I have a question for Ryan. How long do you think it will take for a robot to be a supervisor, which is getting the humans?
Right. Well, hopefully never. Hopefully it'll never come to fruition. Another interesting thing is robot supervisor of other robots, right? So that's one more capable robot is helping the other capable robots. Yeah, let's hope that doesn't happen.
Any other, one last question? Okay, well, my name's Angie. I'm the admin for the Bear Lab, and I just wanted to take a minute for Ryan's friends and family and lab mates who are listening to just say what a great person he's been here at the Bear Lab and how much I've enjoyed getting to know him. He's been here a long time, as he says, and I remember really getting to know him during the first year of his graduate study in the Bear Pro Seminar class, which was online during Zoom and for the first years. And he asked such good questions, and he handled everything with good cheer and good humor at a really kind of weird time in life during the pandemic. And since then, we've worked together quite a bit on the Bear social media. Ryan's been one half of the duo who's put out all the posts on the Bear social media platforms, and he and Dhruv have done a great job with that. And maybe one day some of his work is going to end up as a Bear social media post. We'll see.
Well, it already has been a few times.
Well, after you leave, though.
Oh, good. Hey.
Yes. Look at this. Magic. So anyway, I just wanted to say, Ryan, I've really enjoyed working with you and getting to know you, and I'm so proud of you and happy for you, and Apple's lucky to have you. I hope you keep in touch with us, and congratulations, Dr. Hoque.
Thank you so much.
Angie, I don't think I could have put it any better. Thank you so much for that point. And yeah, he has been a great citizen around here. We're going to miss you a lot. And we hope that you come and visit us when you have your new inventions that we can't talk about. But we're super excited. And I remember, I'm really glad we took that kayak trip.
Oh, yeah.
All right. Thanks. Thank you. Yeah. Thanks, everyone. We have pizza over there, right? All right. Everyone's welcome. Thank you.
Thanks
Thank you, Ryan.
People.